Hey everyone, we are Squad 4 of Mr. Crane's AP Physics 1 class. Today we will attempt to solve question 4 of the 2023 AP Physics 1 FRQ. So at a glance, this problem is worth 7 points with a suggested time of 13 minutes, so we will break this down into 2 parts with 2 different solutions, part A and part B. Then at the end, we'll provide a rubric to explain how you can score high on this problem. So right off the bat, we can take a look at the diagram this problem provides and ask ourselves, what can we infer? Well, this looks like a rotation problem since it is attached to a moving pulley system, so we can assume that rotational inertia is involved, which would mean that angular momentum is likely involved as well, as momentum is always conserved. Now let's break this down starting from the simple concepts. What is rotation? Rotation in physics refers to the spinning or turning motion of an object around a fixed point called the axis of rotation. So take a look at this wheel that is turning around its pivot at the center, and in physics terms that is called the axis of rotation, which allows the wheel to turn. To understand this concept, think of a spinning top. When you spin this top, it rotates around its central point, with the axis of rotation that acts as the imaginary line. Think of kind of like a force that passes through the center of the top from the bottom to the top. And you really can't see it. Like gravity is an invisible force. We feel it all the time, but we don't often pay attention to it. So take this example of this figure skater. Why do they spin faster when they pull their arms in? Well, this is due to the concept of angular momentum given by the equation L equals inertia times angular velocity, and defined by initial and final as momentum is always conserved, they should be equal. Because I equals mr squared, we can plug this back into our equation for angular momentum, and as we can see, the mass does not change, so why is the skater's speed changing? So, as the skater is pulling her arms in, she is actually decreasing her radius, and according back to the equation, her angular velocity has to increase to conserve her momentum. Now that we have some good background knowledge, we can finally start out our problem. So the problem reads, a block of unknown mass is attached to a long, lightweight string wrapped around several times on a pulley mounted on a horizontal axis through its center as shown. The pulley is a uniform solid disk of mass m and radius r. The rotational inertia of the pulley is described by the equation I equals 1/2 mr squared. The pulley can rotate about its center with negligible friction. The string does not slip on the pulley as the block falls. When the block is released from rest as the block travels towards the ground, the magnitude of the tension exerted on the block by the string is Ft. And it is asking us to determine an expression for the magnitude of the angular acceleration in terms of these physical constants. Okay. So I highlighted some of the important things of this this question, and we know that torque in this case is equal to I alpha, or force times radius. And as Zainab has broken down this lovely drawing for us, we can ask ourselves, where is the force acting on? So it is clear that the force is acting on the force of tension times the radius. And we're given the inertia, which equals 1/2 mr squared, so this is really just a plug and chug back into the torque equation to solve for alpha, or angular acceleration of the disk. And this will be force of tension times radius equals 1/2 mr squared times alpha, and the r cancels out. So we get this after doing the algebra. So we have used all the physical constants that are appropriate, and we have found angular acceleration, so this is the answer to part A. So you can score high on part A if 1. You identify the force of tension applied on the block by the string, and 2. If you notice the moment of inertia of the pulley equal to the torque multiplied by the angular acceleration, which we did, and 3 points earned if you substituted the right quantities, and 1 point is earned for providing the right answer. Here is what a sample response that scored full points will look like.
So let's read part B real quick. Part B reads, scenarios 1 and 2 show 2 different pulleys. In scenario 1, the pulley is the same as a solid disk, referenced in part A. In scenario 2, the pulley has a hoop with the same mass and radius as the disc. Each pulley has a lightweight string wrapped around it several turns and is mounted on a horizontal axle, as shown. Each pulley is free to rotate about its center with negligible friction. In both scenarios, the pulleys begin at rest. Then both strings are pulled with the same constant force Fa for the same time interval, change in time. Right. So this causes both of the pulleys to rotate without the string slipping. After time interval change in time, the angular momentum of the disc is equal to the angular momentum of the hoop, but the rotational kinetic energy is greater than the hoop. So now the question, right, is, I'm not going to read the entire thing, but the question is basically asking that explain why the change in angular momentum for both pulleys is the exact same, and also explain why at the same time they're both the same. Why is the rotational kinetic energy greater for the disc? Let's write down some known facts.
So Mohammed's mic stopped working, so I'll be explaining what he solved. So we know that the discs are equal forces and they're constant, as solid disk mass 1 is equal to solid disk mass 2, so therefore they are also equal. So this is another torque problem. So there are two things we have to address for part B. We have to address the change in angular momentum in both pulleys and the rotational kinetic energy. So this is more of like a paragraph-based response. And these are known facts. So we also know that torque is equal to basically change in momentum defined by T equals radius F times sine theta. And we also know that momentum should always be conserved. So let's get to the argument. How are they the same? So for an answer, we could say that because there is the same force given acting on the same disks at the same distance, then we can say that the torque is the same, therefore the angular momentum is the same and conserved. So let's talk about the second part of part B, which is asking for the energy. And we'll need to prove that kinetic energy is higher or greater for solid disk than the hoop. So we know that kinetic energy for rotation translates to 1/2 omega times inertia squared. Sorry, I forgot to square that in the drawing, but it's squared. So like we said previously, they both have the same angular momentum, so we kind of have to build our argument around that. So for hoop 2, we can literally say that it has a greater I because the mass is farther from the center of mass, and as opposed to like disc 1, who is like the mass is literally on top, like next to the center. And so we can see that hoop 2, the mass is very far from the center, and going back to our equation, K equals 1/2 I omega squared, this would mean that the argument here is the greater mass distance from the center means greater inertia. And because momentum's conserved, this guy is not going to be spinning as fast as we see in the equation, that this omega will be significantly slower to, conserve momentum. Okay, so in our answer, we can say that because both have the same I omega, but the hoop has a greater inertia because initially the mass is further away from the center or the axis of rotation. Therefore, the hoop will have to have a smaller omega speed, so it spins slower than the disc, meaning that the kinetic energy will be slower or less than the disc. And now because omega 1 is greater than omega 2 of the hoop, the solid disc will have more rotational kinetic energy. So we decided this is how you can earn all the points for this part of the problem, and this is the sample response. I'm not going to read it just to save time, but this would be a full scoring response. And most of the work should be explained in the video, so this is very self-explanatory. So this problem allowed us to successfully look into rotation and angular momentum from part A, as we just plugged and chugged with the equation and the givens given to us to find the angular acceleration using the physical constants given. And part B is very similar to what we learned prior to learning part A. We just kind of took the ideas of conservation of momentum and we applied that to rotational momentum. And we kind of use that equation concept to explain how the change in kinetic energy can be different